Okay guys, in this video we're going to quickly lay down some graphs of exponential functions using what we know about the shape of the parent function. And so we are going to, in this set of examples, use the parent function y equals 2 to the x in order to quickly sketch all of these other powers of 2 here. But basically, what can we use about the parent function in order to determine some things about the transformation? So first things first, let's write a little thing up here on our papers here. When we talk about the parent function, okay, what we're talking about in terms of an exponential function is any function that's of the form y equals b to the x here. Now we lay down some stipulations. We say that b is not equal to 1 because 1 to any power would be just itself. We say that b is not equal to 0 either, but we could also say that b is just simply a positive base. And so have to exclude this altogether. We could say b is some positive number. But basically, we can see that as long as our base is positive, then we get some basic shape that happens with all of our exponential functions. So what I've done was I've actually put in the Desmos here, y equals b to the x, and in this case, b is equal to 2. But what you can see here is just that as we start to plug in more and more x values here, 0 goes to 1, 1 goes to 2, 2 goes to 4, we can see that every time x gets bigger by 1, our base is doubling every time. And this is a direct product of our base being a value of 2. If we were to change our base instead to a value of 3, we could see that every time x gets bigger by 1, we're actually multiplying by 3 every time. And that as we go to the right on our graph, our point heights on the original graph are tripling each time. Excuse me. So as we look at an exponential function here, we can see that all exponential functions have the same basic shape. It's just that the bigger this base gets, and let me see if I can zoom out for you here, the bigger this base gets, then the faster our function grows. But in terms of the same basic shape, they all have the same basic shape if it's a parent function. So that shape would be that we have a horizontal asymptote at y equals 0. I'll put that in here. You can see that down here. And then 2 points that we tend to always put in our table are 0 and 1, at least for plugging in x values. And the reason why is because at least with the parent function, when you take b to the 0 power, you always get 1. And so regardless of the base, you can see that that point 0, 1 is relentlessly on this graph. Even if it's a decay function, it is going to be on this graph, 0, 1. Now, the other point that I always like to point out, I'll drop my base at 2.4 right here, is just this point 1, 2.4. And so generally speaking, we can see that if you plug in 1 for your power, you're going to get b to the first power. In other words, you're just going to get whatever the base value is. And so some things that I want to make sure we write here about our parent function, just really quickly up here next to parent, is just simply this. Our parent functions, if they're exponential, okay, if b is greater than 1, if we have a base greater than 1, then it's going to have an asymptote on the x-axis at y equals 0. That's one of our 3 critical points. We say 0, 1 would be on our graph here, 0, 1. And then the other point on our parent function here would be 1, b. And so I'm just going to say that this is arbitrarily at some arbitrary height that represents b. But we say if b is bigger than 1, then we're going to have this growth function right here. If b is less than 1, we still have an asymptote on the x-axis, and we still go through 0, 1, which I'll label 0, 1. Let me label it on the left side here. 0, 1. But if b is a fraction, okay, a proper fraction, then we're going to see that 1, b, because b is between 0 and 1, it's actually going to be 1, whatever b is, which is going to be lower than what I started with here. We could see that this would be an exponential decay function. So we're going to say growth. If b is bigger than 1, decay if b is between 0 and 1. So that being said, what we're going to be doing is we're going to be graphing transformations of functions. And so let me put it to you this way. In terms of transformations of our exponential functions, they're going to come in this form right here. A times b. b is the only thing being raised to the power here. It is our base, but to the power of x minus h plus this loose constant k here. So let's write down a few things we know here. We say a is stretch and shrink. Shrink. Okay. We say if a is negative, it's an x-axis reflection. Okay. Our h value is horizontal translation, left and right shift. And then our k value is vertical translation or vertical shift. Now recall about h values, using what you've known about them in the past, we can say that they seem backwards. That is, when you look at the form of the function up here, we say it has a subtraction sign in front of it, and so it's going to represent itself opposite of what it really is. So in terms of graphing these right here, we'd say, well then, if I wanted to graph f of x equals 2 to the x plus 3, then really what we'd start with is the parent. So the way this works is always graph the parent function first. We're going to say that the parent function, I'm not even going to use f here, I'm going to say y equals 2 to the x power. So what do we know about 2 to the x power? Well, what I would suggest is I need to know at least 2 points on the graph and the asymptote. The asymptote is automatically, because it is the parent function, always at y equals 0 here. And we would plug in 0 and 1. So we say 2 to the 0, well, that's just 1. And 2 to the first is 2. Well, then our parent function goes through 0, 1, and 1, 2. We say this is all our parent function really does here. So if we were to compare this now to this graph right here, we say what is different about it? I want you to recognize that this 3 here, because it's not bundled up in the exponent with our x, this is a k value. And so technically we could say that our h value up here is 0 since it's 2 to the x minus 0. And we say that our a value out in front here is technically a 1, and so we're really not messing with anything there either. We would say that this graph is just going to shift up 3. So in terms of shift up 3, will that affect the asymptote? Well, it certainly does affect the asymptote. And in terms of an h and a k value, in terms of exponential graphs, the asymptote will always be at the height of whatever the k value is. And that's because we'll shift it up or down from a height of 0 in the parent function. The other two things we need to move are these 2 points right here. And so because I'm going to move those up 3 also, they would belong here and here. We could say that this new graph looks like this if I could get it a little bit more clearly drawn. So in terms of what these 2 points are right here, you do need to include them. You can either label them on the graph or you can label them in a table, but we're certainly always going to label these 2 points in the asymptote. That'll give you 100% grade on your graph here. So this exponential function, the only thing that I want to mention here before we go on to the next graph here is basically the domain. First things first, all exponential functions, no matter what you plug in for a power up here on your x, you're always going to be able to take your base to that power. And so in other words, you'll always get a y value back. And so looking at your graph, we can easily discern that it goes left and right forever and ever. And it's always defined for any x value. It's negative infinity to infinity. But in terms of range, we can see that we actually start just above this asymptote here and go up forever and ever. And so in that case, we would say that our range is starting at a height of 0 and increasing to infinity forever and ever. Sorry, not at a height of 0, height of 3 to infinity. I was looking at the parent function. So let's take a look at the next one here, f of x. But in this case, you can see that we still have the parent function 2 to the x power, which is this green graph over here. What we want to do is graph it if it had shifted left 1 and down 4. And so first things first, what I'm going to do is I'm going to say, well, knowing what I know about the parent function over there on the left, which I've already graphed over there, I would know that my asymptote would shift down 4, and so it would be y equals negative 4. And with respect to these 2 points here, we had them at 0, 1, and 1, 2. But in this case, since I'm going left 1 and down 4, we would go left 1, 1, 2, 3, 4. This new point would be here, and likewise, this would go left 1, 1, 2, 3, 4, down 4 would be here. And so this graph, very easily drawn, is just this exponential function right here where we say that our asymptote is at y equals negative 4. And just by counting our points here, we'd say this is negative 1, negative 3, and this is 0, comma, negative 2. Okay. So domain and range, really quickly we'll state these. We say since it's exponential, period, it's always negative infinity to infinity for domain. And then the range is always going to be either above or below the asymptote, in this case above the asymptote. So just above negative 4 there and going up forever and ever, but not including negative 4. So let's take a look at one last graph here, and you'll notice that our parent function's on the other page. Oh no. So let's put our parent function in here. Parent function, again, remember, is just if you were to make your a value a 1, and your h value a 0, and your k value a 0, okay, then you would end up with this very basic parent function, which is just 2 to the x. So we would say, knowing what we know about 2 to the x power here, let's see if I can draw, maybe click on this, see if that helps. We can draw our asymptote in here at y equals 0. We know that it goes through 0, 1, and in this case, 1 comma the base, okay? And so that's going to be right there. Since this is our parent function, though, we say, looking at this, I notice that I have a negative out in front and then a plus 5. Now, one thing I want to mention about this negative out in front is that this is an x-axis reflection. You say, well, how do you know this? Well, because 2 reasons. One, the negative is not in front of the x explicitly up here, so it's not a y-axis reflection. And also, this negative right there, if I were to take everybody times a negative 1, that would make this a positive 2 to the x and negative 5. But that negative would come over here, and you would see that that negative is manifesting itself as really making all of your f of x values negative or your y values negative. And in that case, if you took a graph and made all of its y values negative, you could see how it would flip over this x-axis here. So basically, a negative out in front you can see that this is going to open downwards, you could say, but it's going to cause our graph to reflect over the x-axis, and then we're going to shift up 5. So let's start with our reflection. We might have to have a couple sketches on this one, but our reflection would map downward here. We would say everything would be reflected across the x-axis. So we would have this graph that is still growth, but in a negative fashion. And then what we're going to do is we're going to grab everything on this graph and shift it up 5. So I'm going to have to change my color again. You might use colored pencils or something to distinguish between them. But I would say that my asymptote is, going to shift up 5. Here it is. Okay, I didn't really use a different color, did I? Let's try this again. How about, there we go. Unmistakable on this one. We would say that the asymptote is at y equals 5. And I know that because these points are just shifting up 5, I'll go 1, 2, 3, 4, 5. They would be here, and I can tell that this one would lie here respectively. We could see that we get this exponential function that stays really close to its asymptote and then grows negatively without bound, and whose domain is, of course, negative infinity to infinity, but its range looks like all values below the asymptote. So we're actually going to say starting down at negative infinity and going up until we get to 5 there, this would be the range of our function. So I want to be able to easily make these graphs just by being able to graph the parent function, its 2 points and asymptote, and then shifting them around, stretching if we need to, and reflecting if we need to. Cheers.